Alrighty, guys. Here's quarter 3, week 5 AP Stat Need to Knows. So the first question wants us to describe a measure known as resistant or non-resistant measures of center and spread. Okay. So what is meant by being a resistant measure of center and spread? Which values are considered resistant? All right. So first we need to describe whether or not the mean is resistant or non-resistant. All right. So the mean we'll consider to be non-resistant. All right. So essentially what that means is that because the mean is an average of the data set, okay, if there's applied any outliers, okay, it will generally impact that mean, okay. So for example, say we have numbers 1, 2, 3, 4, all right. If I try to find the average of this, I just sum up all of this, okay, and then divide it by 4, which will probably give me a very small number, all right. But what if I had another set, 1, 2, 3, 4, and then add 100 as an outlier, okay? Because we added that 100, that mean will be significantly different, all right, than when we calculated the mean from the previous set, okay? So essentially, the mean is indeed impacted by outliers. So that means it's non-resistant, all right? It will indeed change, okay? So what about for median, okay? So for median, it is resistant, all right? So for median, it is resistant, okay? So let's use the same example that we did there, okay? So if we're trying to find the median of this set right here, okay, the median will be in between 2 and 3, okay, which would be 2.5, okay? Here, we added an outlier of 100. If I try to find the median would be the middle number, which would be 3, okay? 2.5 is not that far away from 3, okay? So basically, for the median, all right, because you're trying to find the middle, all right, the position of the data, all right, rather than the values themselves, is not affected by outliers. So again, if you realize that middle point wasn't generally affected because it went from 2.5 to 3, all right, so the position won't be really affected, all right. So what about for IQR? Okay, so interquartile range, okay. So for interquartile range, similarly as median, all right, you will say that it is resistant, okay. So the interquartile range, or your IQR, okay, is when you subtract your quartile 3 by your quartile 1, okay? So it essentially will not be affected by outliers or extreme values, all right? Because again, it's similarly trying to find that position, okay? And it only changes within the central portion of the data. So again, only the central portion of the data will be impacted for that normal type distribution, which will be more of that mean, okay? So what about for range? Well, your range is calculated by your maximum value minus your minimum value, all right? And your range, because your maximum value can vary when it comes down to outliers, the range will be non-resistant, okay? So again, it will be non-resistant. And we can use our previous example to show us that. If we had this set, the range would be 4 minus 1, which is 3. But if we looked at this set, the range would be 100 minus 1, which would be 99. 99 is a far ways from 3. Okay? So the range is non-resistant. It will indeed be impacted. All right? So finally, what about standard deviation? Okay? So standard deviation. Okay? So for standard deviation, it would be, what do you think? It would actually be non-resistant, all right? So again, it would actually be non-resistant, okay? The reason why it would be considered non-resistant is that since the mean is sensitive to outliers and the standard deviation involves squaring the difference from the mean, okay, outliers can be disproportionate, all right, based on what our data set looks like, okay? So again, for standard deviation, it will be considered non-resistant for that reason, okay? So what we're going to do is that we're going to answer this question. So it says to be resistant, it means what? Okay, so resistant means that the value is not significantly affected or impacted. All right. So again, to be resistant means you're not significantly impacted. All right. So it means that you can resist change. All right. So what about our next question? So the next question wants us to transform data sets and try to utilize how operations that affect mean and standard deviation of a data set. So we were given these three data sets that depict the means and the standard deviations. The first question says, what is the mean of this scenario? Okay, so let's calculate what that mean would be. So the mean will be calculated by doing 2 multiplied by the mean for A, which was 25, then 3 multiplied by the mean for B, which was 45, then negative 4 multiplied by the mean for C, which is 60, and then plus 10. Okay, so now we're going to go ahead and calculate. So 2 times 25 is 50, 3 times 45 is 135, negative 4 times 60 is negative 240, and then we bring down the plus 10. And if you calculate all of this, you get negative 45. All right, and that would be the mean of that scenario. So now we need to try to find what's the standard deviation of the same scenario, assuming independence. All right. So when we're calculating the standard deviation, guys, we're basically going to calculate the square root of variance. All right. So we're going to do the square root of variance. Variance is when we're going to apply based on our scenario. We're going to multiply the 2 by the standard deviation for each set and then square it. Okay, so that's how you calculate variance. All right, so we're going to do 2 multiplied by the standard deviation for set A, which was 7, then square it, then plus 3 multiplied by the standard deviation for set B, which was 8, then square it, then add that to negative 4 multiplied by the standard deviation for C, then square it. All right, and that's it. We will not apply where we're going to add that 10 because, again, that 10 will not impact our standard deviation. All right. So essentially, guys, all right, what I'm going to do is just calculate all of this. When I calculate it, I get square root of 1,172. Okay. 1,172, which is equivalent to 34.26. All right. So again, guys, just like that. So let's do the final question, guys, and the final question is going to be quite lengthy. All right. So the question says, what linear transformation rule that's represented in the form y equal ax plus b, where a is technically representing that slope, okay, and b is technically representing that y-intercept or whatever you're starting at, okay, would apply to achieve a mean of 120 and a standard deviation of 20. So in this case, guys, we're trying to find what rule we can use to transform any of our sets to give me this. In this case, it didn't tell us which set we're going to apply it to, so let's apply it to set A. So we're going to try to change set A's mean and standard deviation to get this new mean and this new standard deviation. All right. So to do that, we need to try to set up a form that looks like this, where the mean for the new scenario, okay, is equal to some variable A multiplied, okay, by our old mean plus some constant B. Okay, so we know that our new mean was this value right here, 120, and that's going to be equal to A being multiplied by my old mean, and my old mean for set A was 25. Okay, so multiply by 25, and then we're going to rewrite that constant B. Okay, so now we can expand, and now we have 120 equal multiply A times 25. We have 25A plus B. Okay, but our problem is, guys, we don't know the value of A nor B. All right, that's our main problems. Okay, so what we're going to do, guys, is that we're going to try to facilitate how can I find those values. Okay, so here's where the standard deviation comes into play. So what you're going to do is that you're going to manipulate the formula for the standard deviation. So you're going to say the new standard deviation is equal to the absolute value of some variable, which we're going to consider A, similar to that variable right here, okay, plus your old standard deviation, okay, so, or rather times or multiplied by your old standard deviation, okay. So when I'm doing this, guys, all I'm going to do is just substitute some values, okay. So I'm going to say new standard deviation was 20, that's what we saw right here, and the old standard deviation for set A was 7, okay. So in this case, I just go ahead and substitute. So I have 20 is equal to the absolute value of A multiplied by 7, okay. And then to find A, all I need to do is divide by 7, okay. So A, or the absolute value of A, is equal to 20 over 7, all right. So when we apply the absolute value, it just makes this number stay as a positive. So A is 20 over 7, okay. So all I have to do now, guys, is substitute that value into my equation and then use that equation to find the value of B. Okay, so when I go ahead and substitute, I will now have 120 is equal to 25. I replace the A with this 20 over 7 plus B. I go ahead and multiply. The denominator here is a 1. So I have 120 is equal to 25 times 20 is 500 over 7 plus B. Okay, so all I need to do now, guys, is just go ahead and subtract 500 over 7 from both sides of the equations. All right, that gets canceled, and my B value is equal to, so I'm just gonna just plug that straight into my calculator. Okay, so I will do 120 minus alpha y, the fraction, 500 over 7. Okay, and I got 28.571. all right. If you wanted to represent it as a fraction, you press mode and then go down to where your answer, all right, is represented as a fraction. So let's see if I click auto, if that changes it. All right, so it represents it as a fraction right here, okay, and it's already simplified for you. Okay, so this can be that decimal that we had there, or 340 over 7. All right, so all I'm going to do now, guys, is just go ahead and substitute those values for A and B into the general form y equal ax plus b. So when I substitute that, I'm going to now have y equal, my A is 20 over 7 x, all right, and then my B is positive 340 over 7. All right, so again, guys, just like that. You can use the decimals if you want, but I prefer to use the fraction. It makes it a little bit more accurate. Okay, so let's try the next question. All right, so the next question, it says we're trying to interpret residuals. All right, so we need to use linear regression equation to describe the residual given the data set. Okay, so I'm going to try to separate this. Okay, so it says the following Minitab output provides the least squared regression line, LSRL, to predict the price of a used bicycle in hundreds of dollars based on its age in years. Okay, define the variables, the explanatory variable and the response variable. Okay, so the explanatory variable is whatever your experiment is based upon, okay, or your x value. Okay, so in this case, guys, it says that my experiment is based upon its age in years. So the bicycle's age in years. Okay, so now we're going to define the response variable. So the response variable is basically what's reacting to your x value, or what's essentially being impacted based on what your x value was or what your explanatory variable was. All right, so what was being responded was the price of the used bicycle in hundreds. Okay, so the price of used bicycle in hundreds of a dollar. Okay, all right, So now let's do the next part. All right. So the next part says, what is the equation of the LSRL given the Minitab output? Okay. So again, your LSRL needs to look like a form y equal, all right, mx plus b. So like slope intercept. Normally, I want you to represent it as y equal b plus mx or plus or minus mx, all right, depending on if your slope is positive or negative, okay? And again, to represent our equation, you always use the predicted value of y, which is represented by y hat, okay? So in this case, we're going to look at the coefficients to identify what the slope and the constant are going to be. So in this case, the constant would be 20. All right. So that means that at 0 years, all right, it costs 20 hundredths of a dollar. All right. So it says that our age, or how we're changing his age, is -2. All right. So that would represent your slope. Okay. So what that means is that as the age, all right, increases on the bicycle, you're losing 2 hundredths of a dollar every time. All right. So let's go ahead and let's try to evaluate the next part. So the next part, part C, says that a 3-year-old bicycle was sold for $1,500. Calculate the predicted price for a 3-year-old bicycle based on the LSRL. Then find and interpret the residual for this bicycle. Okay. So in this case, guys, I'm going to have to use my predicted equation to calculate if what I actually got would have been what I predicted. Okay. So I'm going to replace the 3 for the number of years for x, okay? And I'm going to go ahead and calculate out of 20, -2 times 3 is -6, which is 20 minus 6 is 14, all right? So that means that I would predict 14 hundredths of a dollar, all right? Or $1,400, all right? So, or 1,400, okay? So we predicted something that was smaller than what we actually got, all right? So in this scenario, guys, we basically under-predicted because we predicted less than what we got, okay? So now we're going to calculate the residual, okay? So to calculate the residual, you calculate your actual value, so what you actually got, minus what you predicted, okay? That's normally represented as, so again, residual is normally represented, residual, okay, is represented as y minus y hat, all right, which is y is representing what we actually predicted minus, or y represents what we actually got, and then the y hat represented what we predicted, okay? So we would do 1,500 minus 1,400, and you would get 100. All right, so the residual is 100. So now we need to depict what that really means, okay? So now we're going to depict the definition of what that means, all right? So this is how we will depict it, all right? We'll say based on our LSRL analysis, okay, the residual was shown to be $100, which indicates that our model tends to underpredict. Okay, so underpredict. Okay, a lot of times when you're representing this, you need to talk about underpredict for what. All right, so underpredict for price of a used bicycle in hundreds of a dollar based on age in years. All right. So again, guys, that would be my full analysis or my full interpretation. Okay. So now let's try the next question, all right? So the next question states, all right, that we need to try to identify types of tests and experimental designs vocabulary, okay? So the question says, a doctor observes the relationship between the number of hours and of exercise per week and the cholesterol levels in patients. The doctor notices the patients who exercise more tend to have lower cholesterol levels, while those who exercise less tend to have higher cholesterol levels. Describe whether this is an experiment or observational study, okay? So based on the fact that he's not manipulating any confounding variables, this will be considered as an observational study, okay? Observational study, okay? Because again, he's not trying to control anything, he's not trying to manipulate anything, all right? So he's just seeing if there is some type of correlation with one another, all right? So essentially, if you wanted to define why, okay, or describe why, here's a perimeter that you could state, all right? You could say the researcher, all right? And we're going to call the researcher the doctor, okay? All right, so the doctor observes only the relationship between exercise and cholesterol levels. Without manipulating the experiment, or without manipulating anything, all right? So without manipulating any variables. So let's say any variables, okay? So what about part B? So part B says, based on this observation, what would be an appropriate conclusion the doctor could make, all right? So we could state that the doctor, all right, could state that there is an association, all right, an association or correlation, okay, between exercise and cholesterol levels, all right, but not a causation, okay? If you had manipulated or controlled anything, all right, or added any treatments, then we could say there's more of a causality, all right? But because we didn't manipulate anything, we can only say there's an association or correlation between exercise and cholesterol levels, all right? So let's try the next one, all right? So the next one, we're trying to evaluate binomial events. So it says mathematically model probability associated with binomial scenarios. So it says a company manufactures batteries, and it is known that 85% of the batteries met the quality standard, while 15% are defected. Assume each battery is tested independently. Answer these questions. So firstly, let's try to represent this as good batteries, all right, and bad batteries, okay? The bad ones are the defected ones. So we have 85% of them are good, so that's same as 0.85. Okay, and then 15% of them are good, are bad or defected, and that's represented as 0.15. Okay, so what we're gonna do now, guys, is go ahead and try to answer the first question. So it says, if 50 batteries are randomly selected, what's the probability that exactly 40 of them are good quality? Okay, so we're picking or selecting 50 batteries, and we want to make sure 40 of them are good. So we need to evaluate the probability of being good, which is 0.85, and I need 40 of them to be good, okay? But if I selected 50, 40 of them are good, that means there's 10 of them that aren't good, or 10 of them that are bad or defected. So I need to use a probability that they will be defected, and that needs to happen 10 times, okay? However, there's multiple ways that we could represent this, because again, the first one could be the one that's bad, all right, and then the rest of them are, and then 40 of them are good, or the first one could be bad, and then the second one is good, and then the third one is bad, and then the remaining 28 of them are good. There's a lot of ways you could represent this. So you need to use a choose function that's going to represent the amount of ways. So you're going to have 50 choose 40 things, okay? So this is the same as just saying 50 factorial over 40 factorial, 10 factorial, but it's a lot easier to use your calculator to calculate this, all right? So I will first calculate the choose function by pressing alpha, y, go to the right side, go down to n choose r, all right? And then we're going to put 50 choose 40, all right? And then I'm going to now multiply that by 0.85 to the 40th power, and then multiply that again by 0.15 to the 10th power, okay? And I got 0.088, so let's just say 89, okay? So let's just round to 3 decimal places. It didn't tell us how to round it, so we're just going to round to 3 decimal places, all right? So let's try the next one. So the next one says, if 120 batteries are tested, what's the probability that at least 100 of them are good quality? All right. So in this case, you could either have a good quality battery or a bad quality battery. So we're going to use a binom CDF, or rather binom. The reason why we're going to use CDF is because we're trying to say that at least 100 of them are good. All right. There's 120 batteries that are tested. So I need to do all the numbers from 0 to 99, cancel those out so that I can only look at 100 or more. Okay? So that's why we're going to do a CDF, because you're using a cumulative amount. All right? So when you're using binom CDF, these are what the functions look like. Okay? Where the first function depicts the trials. So in this case, we have 120 batteries, so 120 trials. Okay? And then we're going to look for the probability that they are good, which is 0.85. So 0.85. And again, when you're doing a CDF or binom, it's calculating from 0 up to a certain number. Because we're trying to say at least 100. At least 100 means you're trying to evaluate 100 or more. Because this is more of a counting function, it can only do from 0 up to 99. And then you do 1 minus that amount to get all the things above 99. All right. So when I calculate this, guys, so up to 99, okay, then I do 1 minus that answer, so second function, the minus sign. All right, I get 0.744. Okay, I'm gonna again round to 3 decimal places for this one. Okay. So let's do the final question, guys. So the final question says, what's the probability that the first defected battery appears on the 10th test? Okay. So in this case, guys, we're saying that the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, all right, all of these were good batteries, okay? And the first time I see a defective battery was on the 10th, okay? So in this case, guys, I need to look at the probability that all of these are good. So all of these are probability of 0.85, and it's happening 9 times, so it's 0.85 to the 9th power. Then we had a defective battery, so that was 0.15 to the first power. All right. So when you calculate this, okay, I would do 0.85 to the 9th power, then multiply by 0.15. Okay, and I got 0.035. Okay, so that's the answer. So what we're going to do now, guys, I'm going to show you another way you could represent this. So you could represent this by doing a geometric PDF, all right? So you could say second function vars, go to GeoPDF, all right? And then you're going to be evaluating the probability of actually getting a defected. So 0.15, okay? And then that needs to be on the 10th number. So this is looking for specifically when the 10th time is defected, okay? And that would be the same probability as what I got for the previous question. All right. So let's do the remaining questions, guys. Let's do the rest. Okay. So the next question says we're trying to calculate outliers and identify and classify any outliers. Okay.